So we have two new terms. We have embedded systems and we have general purpose computers, and both are actually computers, but embedded system is a special type of computers. It is actually any device that includes a programmable computer. Any device, let me write that down. Any device that includes a programmable computer but itself not intended to be a general purpose computers, not intended to be a general purpose computer. So of course embedded system also a computers, but they're not intended to be a general purpose computers. There's a computing facility inside a device, embedded inside a device, for example a microwave, an AC, an ATM machine, and hundreds of other examples. So what's the basic difference between a general purpose computer and embedded system? General purpose computers are developed for general computing without taking into consideration a specific task, but embedded systems, they are designed in constrained conditions. We have constraints like space. In embedded systems we don't have a lot of space. We have constraints like memory. We have cost constraints. We will be explaining these constraints. I will be explaining these constraints later. So a very basic definition of embedded system. Let me try to formally define embedded systems. What are now embedded systems? They can also be called as applied computer systems. They are actually known as applied computer systems. Or a more formal definition may be embedded systems are systems. They are systems that have embedded software, that have some software that we call as firmware. Embedded software, they have software known as firmware, plus they have some application specific circuits, hardware. They are combined and they are designed to perform a single task with the best possible efficiency. So the definition may go like this: embedded systems are systems that have embedded software and computer hardware, which makes it a system dedicated for an application or a specific part or a part of a larger system. For example, a microwave, an AC, speedometers in our odometers in our cars, music systems in our cars, and there are lots of examples like printers, modems, etc. Simply software plus hardware plus a dedicated task. Will constitute our embedded system. Before moving on, we have defined three terms now. We are very much familiar now with microprocessors, processors, computers, and embedded systems. Before defining our last microcontrollers, let us discuss some more features of embedded systems. And before doing that, let me give you a few more examples of embedded systems. The application domains where these embedded systems are used. They are used in medical equipments. Any medical equipment you can think of where you think there is some sort of computing needed. For example, X-ray, a digital X-ray machine. Or maybe digital blood pressure monitors, BP monitors, glucose monitors. Many other examples. They are used in banking. In banking sector, I have already given an example. The best example in banking sector is an ATM machine, cash withdrawal machine. There may be also various security gadgets that are used in banking. They are also embedded systems. Currency counters, they are also embedded systems. In computer peripherals, like printers. We might have embedded systems in keyboards. Another example is from networking. We have devices like modems, embedded systems. As they say, हम embedded system से गिरे हुए हैं. We have embedded systems in handheld electronics. Like modern digital computers, like smartwatches. There are a lot of embedded systems in our cars, in automobiles. For example, music systems. For example, the system which is actually used for ABS, anti-lock braking system. We have embedded systems also in factories. We have in aviation, in our aeroplanes. We have embedded systems in military, in defense, for example, thermal goggles. Hundreds of other examples are there. We have in robotics. Okay, that's fine. I think I have given a lot of examples. By now, you might have got the big picture where are embedded systems. Now, let me move to our next topic. Why is embedded system design different than design of general purpose computers? Why is embedded system design different? Why is embedded system design different? Or we can say it's more challenging. Why is it more challenging than the design of general purpose computers? Because of various constraints we have. The constraints which are not many of these constraints are not present in the design of general purpose computers, but in embedded system we have various such constraints, and because of those constraints it's more challenging. Embedded system design is more challenging. Number one constraint: in embedded system we have varied types of standard and non-standard IO devices. What do I mean by this statement? Varied types of standard and non-standard input-output devices. You may see in general purpose computers, the input-output devices we have to connect to a PC are very standard, in the sense that we may have to attach a keyboard, a modem, a mouse, maybe a joystick, or a monitor and a printer. very standard input output devices. We already know about them. But in embedded systems, the types of and the quantity of input output devices varies greatly. In the case of AC, the input device is our IR remote and also a temperature sensor. Output is maybe a fan or a cooling or heating rod. Also an LCD. There also may be some LEDs. In terms of in the case of ATM machine, input is an ATM card. Input is from internet. Output is in terms of motor movements, which actually give us the cash. If I can take an example of some other input output device, for example a blood pressure monitor. Input is again different. There may be a pump, there may be some sensor which is used to actually detect the blood pressure. In some other example, maybe in a smartwatch, inputs are again different. So in embedded systems we have varied types of inputs, and they may be standard or they may be non-standard input output devices. So naturally the design of embedded systems becomes more challenging than the design of general purpose computers. First thing. Second thing, we have power constraints. Power constraints in the sense that most of the embedded systems, it may not be feasible that we keep them plugged into the mains AC always. For example, a blood pressure monitor runs on batteries. We can't keep it plugged into mains AC. Some of the embedded systems, they may be deployed in the middle of the sea. They may be deployed underwater. So we cannot have a constant power source. So there are power constraints. Number 3 is limited memory. Actually, embedded systems, since the computer is embedded in a device, we have limited space, limited memory, limited computing facility. So actually we cannot install a full-fledged computer inside our embedded systems. We cannot install a full-fledged computer inside our washing machine. I'm talking about digital washing machines. We cannot install a full-fledged computer inside an AC, inside a microwave, inside a blood pressure monitor. So we have very limited computing facility inside that computer, very limited memory, very limited space, and there are also constraints. Embedded systems, again, they may be deployed in extreme weather conditions, maybe in space, maybe underwater, maybe on glaciers, maybe in volcanoes. And also another thing, embedded systems, we have gone through various varied types of input output, standard and non-standard power devices, power constraints, limited memory and computing facilities, extreme weather conditions. And then we have since embedded systems, they need to be real-time systems. Embedded systems, we may say, they are reactive in nature. Again, let me take an example of AC. What actually AC does, we give it the input, we give it a set temperature using our IR remote, then it actually tries to decrease or increase the temperature of the room to that set temperature, and it constantly checks the ambient temperature of the room through a temperature sensor. So it actually reacting to some parameter of the nature, maybe temperature, maybe pressure, maybe some other parameter of the nature, any embedded systems. In fact, every embedded system, most of the embedded systems have sensors which actually detect a physical quantity. And then these embedded systems have to react to this physical quantity. Depending upon the value of this physical quantity, they have to change certain parameters. And that change should actually be in real time. So embedded systems have to be real time. And usually we classify embedded systems at hard real time and soft real time. Hard real time embedded systems. Soft real time embedded systems, both are real time, but in soft real time embedded systems, if we don't meet the deadline, there may be performance issues, but there may not be a catastrophic effect. For example, in a AC, if the embedded system, if the computer we have embedded inside an AC doesn't react instantaneously to a remote, it may be frustrating to the user, but there may not be any catastrophic effect. You may have seen while we change the channels, sometimes our TV doesn't remove instantaneously to our button presses. So it frustrates, or maybe it frustrates the user, but it doesn't have a catastrophic effect. So that's a soft real-time system. It needs to be real-time, but it's not. If it is not, it doesn't have any catastrophic effect. So it's known as soft real-time embedded systems. In comparison to hard, on the other hand, we have hard real-time systems, where if we don't meet the deadlines, real-time deadlines, we may have catastrophic effects. For example, a missile launcher. There's an embedded system which actually detects an enemy aircraft and launches a missile in defense. If there is a lag, even of milliseconds and microseconds, it may miss the target, and there may be catastrophic effects. So this missile launcher is a hard real-time system, where if we don't react instantaneously, where if we don't meet the deadlines, we may have catastrophic effects. So another thing is they have to be real-time systems. We may have another one, cost sensitive. See, these embedded systems may be used in devices that cost as low as maybe 1,000 rupees. And other thing, they are only a part of the total functionality of the device. For example, in an AC, there are other things also. The computing facility is only a part of it. So while designing the embedded system for an AC, for a microwave, we have to take into consideration the cost of this embedded system, because it's only the part of the total functionality of the device. And if the cost escalates, it actually will escalate the total cost of this device. So that may not be good. And one more thing, that in a common household there may be 5 to 6 personal computers, but there are hundreds of these embedded systems. So embedded systems should actually have a very low cost than our general purpose computers, and some of these embedded systems we have to use in devices which cost very less. For example, we have to use a computer inside a blood pressure monitor, but this blood pressure monitor should not cost maybe more than 2,000-3,000 rupees. So we have to design such a computer that may actually fit inside a blood pressure monitor, and at the same time its cost should also be less. It should not actually consume much power. We have to take care of various types of these constraints. We also have to take care that it should actually be interfaced with various types of sensors, with various types of output devices, with various types of displays. Okay, so these are actually constraints which we don't have in general purpose computers. General purpose computers, we don't have to deploy them in extreme weather conditions. We may not have limited memory there, we may not have power constraints there. We have very standard input output devices there, but here input output devices are non-standard. We have power constraints, we have limited memory, limited computing facilities. They may be deployed in extreme weather conditions, they have to real time, and they are cost sensitive. So embedded system design is actually very different than the design of general purpose computers.